Hello, my name is Ali Siakuhi, and I'm presenting our work on preconditioned training of normalizing flows. An inverse problem is a problem of finding an unknown x given observed data in the presence of noise. In some domains, such as seismic imaging, the forward operator is expensive to evaluate, and we have limited access to training data in terms of the joint or marginal distribution. One way to tackle this problem is via the following objective, which trains a normalizing flow capable of sampling the posterior distribution after training. In this objective, no training data is required, and we only rely on having one observed data y. However, this training requires access to a prior density. It needs repeated evaluations of the forward operator and the Jacobian and the adjoint of its Jacobian. And finally, this gives us a normalizing flow specific to the observation y. So another objective is obtained via conditional normalizing flows, in which we formulate our conditional normalizing flow as a block triangular map between model and data. And after training, we get access to the posterior samples for all the y's. This objective does not involve the forward operator, and it doesn't need to prior density. However, in test time, its success heavily relies on having access to training data that comes from the same distribution. So what we propose is something in the middle of these two different approaches. First, we pre-train a conditional normalizing flow on existing training data, which might be different from the data that we are going to apply in test time. After pre-training, we take the weights and put the weights in another normalizing flow. Basically, we initialize the weights of t with the pre-trained conditional one. We also use the pre-trained conditional network to encode a prior density on a model. And we basically use transfer learning to update the weights. So since we are using transfer learning, we expect to get speedups in training, so less evaluations of the forward operator. And we hope to correct for the errors due to not having access to training data that correctly represents the test data. So this is a toy example. On the left, we are seeing the prior density and the true model we try to recover. And on the right, we see two different likelihood models that we use, one to train and to train a conditional normalizing flow, and the other one to test it using our objective. On the left, we see the estimated posterior densities with and without preconditioning, which are in agreement. And also, both of them are in agreement with the MCMC samples. On the right, we are looking at the objective function with and without preconditioning. So as expected, we gain speed-wise since we are initializing the network with a conditional normalizing flow trained on training pairs, even though they're not from the same distribution as test data. As a final example, here I show results on compressive sensing applied to seismic images. On the left is a true model, and the right is the observed data that we try to basically use to recover the model on the left. Now, on the left is before transfer learning, basically the conditional normalizing flow, and on the right is after transfer learning. Clearly, we have corrected the errors due to not having high fidelity training pairs with our preconditioning step. Finally, to summarize, our contribution was to combine two objectives to train a normalizing flow to sample from the posterior. We gained speed ups, and we also correct for the errors in training data.